So if we're talking about vectors, one of the most helpful things about vectors is an idea of length. And we want to generalize that to these other vectors we come up with, like if they're made of functions. So we see this in quantum mechanics, where the length of the vector has to do with the total probability, and you better make sure that your probabilities add up to 100%. So the way that we do lengths outside of just geometry and measuring it with a ruler is with a dot product. If I have a vector, and I'm going to take the norm of that vector, well, square roots are annoying, and I'm going to try to avoid that. So I'm going to have this squared. This is vx squared plus vy squared plus vz squared. Or in other words, I am taking a dot product of this vector with itself. And with summation notation, I'm going to write that like this. So this is going to be a very important idea. This generalizes to total probability in quantum mechanics. This is how we make sure things are normalized. And in quantum, we're going to have to use complex numbers. So let's see what happens if I just plug and chug dot products with a complex vector. Let's say that my v has 3 coordinates in it, but now I can have complex numbers. And those are going to be 1, 0, and I. So if I just naively try to take v dot v, I am going to have 1 squared plus 0 squared plus I squared. That's 1 plus 0 plus -1. And that's 0. That is no good. This better not have 0 length or 0 probability. It's pointing somewhere. It has something going on. So we need a better definition of a dot product to account for imaginary numbers like this. And we want length to be positive. Negative lengths don't really come up. That kind of screws everything up if length can now be negative. So if you want things to always come out positive when you're working with imaginary numbers, you better make sure to complex conjugate things. So I am now going to instead suggest that when I dot product these vectors, one of them is going to be normal, and the other one is going to be complex conjugated. So now when I do that, I've got 1 squared plus 0 squared plus -I times I. It's 1 plus 0 plus 1, which is 2. And now that looks very reasonable. The length squared of this should be 2. So I'm going to give you a mnemonic to keep track of that. I am now going to start writing my vectors like this. We call this a ket. You've probably seen this in undergrad quantum mechanics, if only briefly. Different undergrads like to emphasize this more or less. But if I've complex conjugated it, I'm going to write this as what we call a bra. Put those together, a bra ket, make a bracket, and supposedly that is the only joke Paul Dirac ever made. This is nothing too fancy. This is just a mnemonic to make sure I have complex conjugated exactly one time. I have to put together a normal vector with a complex conjugated vector. This is like how if I'm taking a dot product, I can write that out with matrix multiplication if I want, even though it's kind of overkill. So if I write all of my vectors as column vectors, I get to dot product it, where I have to transpose it, and then I complex conjugate all that. So the bra is nothing more than complex conjugate plus transpose. When you put those together, that gives you a number. So we are going to apply this with more vector ideas. And one of the first things we can do with that is rotations. So I would like to rotate something I'm going to have some vector v, and I rotate it to a new vector w. And if I'm going to characterize a rotation, so I'm going to give you a geometric rule about I take x, y, and z axes, and I rotate them somewhere new. What's special about a rotation is that no matter how I rotate things, the angles between things stay the same, and the lengths of things stay the same. I want to preserve lengths when I rotate. Now, reflections do this too. We are later going to talk about how to rule out reflections from this, but the key idea with the rotation is to keep all your lengths constant. So, if I want my lengths to stay constant, that means my length of my resulting vector, the w, which I can now write with our upgraded dot product, which we call an inner product. It's a dot product. I don't think I ever said that. But if you see inner product, it just means dot product, where we might be using some of these extra rules. This length better be the same as the old length. So let's try to equate these a little bit better. So the w is the same thing as r acting on the original vector. But then, when I flip it around to the bra, I have to transpose and complex conjugate. So the r that I wrote is going to be transposed and complex conjugated. So if I transpose and complex conjugate together, I'm going to write a little dagger for that. You might see that being called a Hermitian adjoint. If you just say dagger, people know what you mean. So as I put these together, and I have in the middle r dagger r acting on v, better give me my original length, then all of this in the middle better not do anything. This better be equal to the identity matrix if I am going to preserve lengths. So this is the all-important rule about rotation matrices. So if we are just doing normal rotations, and again, reflections might do this too, so I'm going to call these orthogonal. What we need is r transpose times r gives you the identity. That's the rule that you preserve lengths. Now, if complex numbers are in play, then we've got to think about complex conjugating too, and we call those unitary. You'll see why later. And then if it is unitary, which is just a word for a complex rotation, now we've got to think about complex conjugating. Now we need to use dagger instead of just transpose. So rotations allow for a really natural way to think about changes of basis, where a lot of the changes of basis we do in physics you can think of as a rotation, where if you have a block sliding down a ramp, instead of using x and y coordinates, you'd like to use rotated x and y coordinates. We're going to practice how to do those changes of basis and see where the linear algebra operations come from, about what you do to a vector versus what you do to a matrix, and how to keep track of that. And this will lead in some very interesting directions later and clue us into Fourier transforms, where there is an important connection there.